Sydney Pacific, it's a very active community, and the vast majority of events center around congregating in groups and eating shared food. In March, the undergraduate dorms de-densified, and then the graduate dorms relatively soon after. In Sydney Pacific, our new mode of living required that we were not allowed to gather, and our student life sort of halted. The spark that became this study actually originated from the grad students in the dorm. They said, isn't there some type of technology or means to understand usage of our shared spaces and risk associated with it? So I thought it's a good question. So I sent a note to 2 different groups, one at the Computer Science Artificial Intelligence Laboratory and another in the Media Lab. I just asked, is there something that we can use that is useful actually like in a dorm? And both responded back immediately and said, not with what we have right now, but here's an idea. Take Bluetooth beacon sources and install them in each of the common spaces. And then we could develop an app that would receive that signal on the phone. From that, you have the potential to back out distance and proximity, and therefore use of those common spaces. I just asked a few questions and had a lot of volunteers. Overnight, we had this amazing team of faculty, grad students, and professionals at Lincoln Lab.
So I think everybody had the same idea at the same time. Everybody carries a smartphone. Oh, what can we use from the smartphone to measure distance? Bluetooth was kind of an obvious first guess. And then the question is, can you measure how long you've been close to someone and how close have you been to that person? I don't think anyone knew at the beginning how hard it was going to be. Bluetooth was not designed for this. If you just stand close to a Bluetooth beacon with your phone and watch the signal strength, it tends to bounce around quite a bit. There are reflections across the wall, there's multi-source, there's all kinds of problems. It turns out that one of the biggest things that degrades signal strength is the human body. What really excites me about this project is the possibility of collecting lots of Bluetooth data to help us build a good mapping between signal strength and proximity. But we already had a calibration protocol for people to collect data in a structured way. However, it was probably a couple hours to actually run the entire protocol. There was no way that we would get people to volunteer. So we came up with a very streamlined calibration protocol. You should be able to run through one of these in about 60 seconds. So the joke I always make is, you're in the kitchen, you just put your burrito in the microwave. You have a couple of minutes, go ahead and do a couple of calibrations.
So I've been working mostly around the app development. It really gets tricky at running these Bluetooth apps because the Google and iOS operating systems are really stringent about Bluetooth code running in the background. So it requires some fiddling around and some rigorous testing. So with iOS, whenever the app goes to a background state, the iOS operating system makes it in a sleep mode. The app is, although running in background, it's not really doing anything. And it's not really trivial to wake up this app and make sure that it keeps recording the Bluetooth data and keeps sending it. In Android, we can do this for every minute. But there is some trade-off with battery usage. It looks like 15 minutes is like sort of a sweet spot where the app can wake up and listen to the chirps and then again go to sleep.
The tricky part is those sensors. You could have an Android phone that is 5 or 6 years old. However, your phone does not have a gyroscope or a barometer. So we have to be able to create a data model so that even if you don't have that information, our backend server can still ingest that and do something with the remaining information. So being able to test those cases is critical. We would just run a bunch of emulators on our computers, but that's completely different because a barometer and a gyroscope don't exist in a virtual machine in a computer. You actually need the physical device. We all did a bunch of testing on the app. Some people have old iOS phones, some people have different Android phones, and that's how we go through it. Everyone tested on their phone, we report a bunch of bugs, but there was a solid 2 or 3 week period where we were just constantly getting a list of tasks and be like, I saw this issue, I saw this issue, I saw this issue. But little by little, we're able to really make some progress to solidify the application.
So phones have complications. Our tile-based solution is far simpler. You have constant transmission power. You no longer have to worry about different device platforms. It doesn't require user input because you can just attach it to your keys and forget about it. So the entire solution is a lot simpler and as a result, a lot more robust. The device will constantly emit chirps. We record those chirps using an external architecture, and you can then figure out which people were in close proximity to each other. So the tile solution allows us to directly compare the additional consequences of using a phone-based environment as opposed to something that's a little bit different.
As a privacy researcher, sometimes I try to think at the worst case scenarios. Sometimes I cannot even predict what that will be because there are so many things that could go wrong. Especially some of the contact traces apps have leaked their entire email addresses. So the fact that we are using an ID that only few people have access to, and the fact that we are not using location, that was something that we had discussed it at length, because removing this kind of information makes it more difficult, but it does make people's identity more secure. And we actually found a good balance. So like we could have gone even further, but the balance that we struck, I think, was good enough.
This whole process is for the students, right? I mean, there are research goals, but part of it is to benefit MIT campus in general. And then much of it is by students because they're the boots on the ground. They're not only the boots on the ground to set up all the infrastructure, but they're also the ones who have to volunteer their own data and download this app. Without these student volunteers advocating in the dorms, this wouldn't happen. Without installers, this wouldn't happen. Without students registering, this won't happen. And then even after they register, without them calibrating, also it will not happen. However, volunteers really need to be invested in too. They have to feel like they're getting something out of it. And a lot of my thinking has gone into how do we make this more efficient and less work for them so that they can enjoy benefits with less cost. And they do what we hope that they will do. I don't know, we shall see, right? Because we're just at the cusp of rolling out Eastgate and Ashdown, and we shall see.
As I talk with my officers about different policies we want to implement or different events we want to run, having the knowledge that the contact tracing study is going on in parallel is very helpful. And the officers that I'm involved with are quite excited. A lot of the questions that other dorm presidents had were primarily privacy concerns, and how the information of the student would be kept and how this information would be used by MIT Medical. Another thing that the dorm presidents were really excited about, they were thinking, yeah, this is a really good thing to start in the dorms, but they were also asking Julie if she'd be willing to deploy this in the labs.
The main objective of the scientific protocol was to evaluate how digital contact tracing would compare to manual contact tracing. And we had 3 secondary objectives in the study. The first one was understanding the trade-offs between more privacy-preserving and less privacy-preserving digital contact tracing methods. Also contributing calibration data to help other researchers understand the relationship between Bluetooth signal strength and distance. And finally, trying to understand user acceptance of different digital contact tracing methods.
I still am amazed we're at the point we are, just about ready to launch the study at full scale, because the team that came together was a set of people who had literally never worked together. And now we're co-developing software, hardware, virtually, and it's been a dream team. The complexity and scale was surprising to me, but you wouldn't know it based on how this has come together in the course of 6 weeks to 2 months. We're currently rolling out to 3 of the graduate dorms, but then 3 of the undergrad dorms as sort of a pilot or a test of what we might be able to do more broadly when undergrads return at a higher level in September. The hope is that we can help keep our community safer through the fall reopening and also provide valuable knowledge on how digital contact tracing technologies can be used more broadly beyond MIT.